Thanks very much, Roman. It's great to have an opportunity to share a lot of the work that has been developed in this group here in Boulder for over 40 years. I've been here since 1990, as Roman said, and we've seen lots of changes. Um, this voltage standard group that Clark Hamilton ran that I joined, there were just three of us. And we were part of a whole division or a whole group that worked on uh, all sorts of sensors and high TC superconducting devices and so forth. And all of that's kind of gone away except for my group that we've renamed as the Superconductive Electronics Group. We also have the former electromagnetic technology division that does all of the transition edge sensors and telescopes. And we have single photon detector groups also doing superconductivity. But I'm going to focus on my work. This is an aerial photo of our Department of Commerce labs. We have the Knoll building over there on the left and the NIST building here. The nice newest one here in the middle is our physical measurement laboratory where we have newer labs, and our biggest clean room is the bottom south third of this. Um, this larger building here is shaped like an old AM uh, radio antenna. It used to be called the radio building. It has a main spine with three arms on each side, and that's from the 1950s. Eisenhower dedicated that. So we have some very old facilities that I do my work in. Um, so why do we do superconductors at NIST? NIST, as Roman said, used to be called the Bureau of Standards, but our mission expanded to do research and technology as well, among other things. And so we have a strong mission to develop new technologies. Um, and our mission is to support U.S. industry and commerce. And in particular, the programs that are of national attention over the last 5 or 6 years have been energy efficient and advanced computing and quantum information. Those seem to be able to be important across administrations. And of course, superconductivity can be applied to those priorities. And I'll tell you a few of those things. We have a very nice clean room. We used to have many small group level clean rooms throughout that old building, and they've all now been integrated into that newer facility and as a shared clean room facility. That's on the left is a picture of Anna Fox, who she builds our voltage standard circuits that you'll see. And we do a lot of superconducting integrated circuits. This picture on the right is a new superconducting sampler that we've developed in collaboration with Bart Van Segbroek here at the University of Colorado, which is just down the street from us here in Boulder. And as you know, the very first product of Hypris Incorporated was a sampler in its day, and that was their main product. So we're rediscovering that to try to make waveform measurements at cryogenic temperatures. So why does NIST work on superconducting electronics? Primarily, it's for quantum voltage standards, and that's what my group has especially done. The detectors group and single photon group here build sensors for astronomy and materials analysis systems using superconducting metal bilayers biased at their transition temperature. They use squid arrays to multiplex the readout of these TES arrays. And I won't have time to go into that, but I do have a slide of that later if anyone's interested. My group has been working with lots of other US programs for high performance energy efficient computing, which we collaborated with Steve Whiteley and others where he is. Quantum computing has been important. We've just recently gotten into that game to try to improve precision measurements of millikelvin superconducting qubits. And so my group is actually making our own qubits and doing measurements of them, and I'll talk a little bit about that. So these days, our group used to be part of the physical measurement lab. Now we're part of the communications technology laboratory, and that's because our Josephson devices mostly are driven with radio frequency signals, but we've also extended some of our signal synthesis devices, not just in the audio frequency range of the 20 to 50 kilohertz, but up to megahertz and gigahertz frequencies. So that will be the bulk of my presentation to you is the devices and circuits that we've expanded up into those frequencies. And one of the other things that we found important as we focus not just on the technologies and building systems, but to always focus on precision measurement and apply our expertise to lots of other programs from my ARPA or DARPA or other uh, organizations that require independent test and measurement to confirm their own devices and things like that. So that's been a big role for my group as well as applying that to control circuits for quantum computing. So these are three of my staff members. Kirsten on the left is a recent hire, and she's testing chips that have come out of the clean room in a liquid helium dewar. Manuel in the middle is actually generating a waveform that he's driving a qubit in the dilution refrigerator behind him. And on the right, Jeremy joined us over a year ago, and he's got a 4 Kelvin microprobe station there that he's using to calibrate an RF Josephson synthesizer. So these are some of the main things that we do on a daily basis in my lab. These are all three different rooms in this larger building. So here's the main outline for my talk. I'll begin with a very brief description of the standard reference instruments that we build. The Programmable Josephson Voltage Standard, or PJVS, operates from -10 to +10 volts DC. The Josephson Arbitrary Waveform Synthesizer, or JAWS, it took 30 years to move that technology, circuits, and RF driven devices to get from 100 microvolts to 4 volts root mean square. That's like 6 volts peak to peak, or actually not peak, just peak. And the frequencies up to 30 to 300 kilohertz. And we're still developing RF sources and Josephson pulse multipliers for quantum-based synthesis to calibrate RF devices and instruments. And we've been able to reach 20 millivolts at frequencies up to 4 gigahertz. So I'll have a number of slides on that. Josephson pulse generators we're using to have a reproducible element to control circuits as control circuits for qubits. And we're basically exploiting the quantized pulses of Josephson junctions. And over the last 2 years, we've been trying to re-optimize sampling circuits to measure RF and SFQ signals at both millikelvin and 4 Kelvin temperatures. So hopefully you can remember these acronyms throughout the talk, PJVS, JAWS, and so forth. And I hope that at the end of my presentation, you'll understand why it's important that we make these quantum-based standards and what is a quantum locking range. So I'll try to show you examples of a quantum locking range. It's a term we made up. There's probably better terms, but it's basically what distinguishes our superconducting circuits from really any other devices you might be familiar with. So what are the main properties that we care about for making these devices and standards? Well, we exploit the properties of superconductors, and they're quantum-based. And why are they important? Well, niobium has zero resistance at 4 Kelvin. It has lower losses, even up to 400 or 500 gigahertz. And this is essential for carrying RF signals and DC signals with zero resistance. For a voltage standard, it's important because the junctions are generating voltages we want to apply to other devices, but we need to connect them without resistance between the junctions. The Josephson junctions are the most important thing. That's really the device my group has exploited for many decades now. They're a weak link between the two superconductors, and the electrons in a superconductor condense and behave as bosonic states that can be described by an individual wave function for the entire material or electrical properties of that material. And that wave function can proximity couple through a barrier here between two different superconductors, and they can interact. And the phase difference between those wave functions is what produces a periodic change in phase across that junction when it's in the voltage state. And that periodic 2 pi variation leads to pulse quantization and fluxoids moving through the barrier and so forth. And so this is the main feature that we now exploit in a Josephson junction, is these quantized pulses. Every time one of these junctions generates a voltage pulse, the area under that pulse is precisely quantized with the ratio of Planck's constant over twice the electronic charge. Now, the shape of that pulse could change, and that will affect waveform synthesis at higher frequencies, but the areas are always precisely quantized. So if you think about this in terms of digital analog conversion, there's no other device in the world that generates quantized pulses. And if you're doing a Fourier transform of some digital representation of a signal, and you use ones and zeros that are integer based, that's exactly the kind of Fourier transform we get when we actually measure the frequency domain of a digitally synthesized waveform. And I'll show you some of those measured signals. In terms of superconducting integrated circuits, we want zero resistance between them. We want to connect these junctions with superconducting layers. As you can see here in this film along the bottom, we have different metal layers, resistive materials. This is a cutaway showing basically a junction with wiring connected to it on a ground plane. So these are important for standards, the sensors, and for advanced computing. So what are the properties that my group especially exploits? Well, we care about voltage standards, and we basically are driving these junctions with DC currents, and first of all, microwave biases at a specific frequency F. And when you do that, and you apply a frequency that's close to the characteristic frequencies of the junctions, you can get quantized voltage steps where they're flat over a range of current, and they generate a voltage that's exactly h over 2e times the frequency and the step number. So that's how the programmable voltage standard works. This range of current is the first quantum locking range I'm showing you today. And you get exactly the same voltage regardless of where you bias it across this step in current. The other feature we're exploiting is pulse creation of these junctions. And on the bottom left, our JAWS system is essentially a digital to analog converter where we generate positive and negative pulses, and the density of those pulses when integrated with a low-pass filter can generate a sine wave. So this is an example of a sine wave with a peak at the top and at the bottom. And this creates a precisely calculable AC waveform at that frequency because those pulses are quantized, and we have precise timing of those pulses using frequency referenced clock generators. This is also exploited in using superconducting networks of junctions, where all these junctions are connected with Josephson junctions to move flux quanta around, or alternatively, you can think of them as generating pulses feeding into other parts of the circuit. And that's useful for our pulse multipliers and Josephson pulse generators, as well as energy efficient logic. So these are the two ways we exploit the Josephson effect for our circuits. Does anyone have any questions at this point before I move on? All right, let's go. So I mentioned voltage standards. These are the photographs of both the PJVS and the JAWS systems for DC and AC audio frequency voltage standards. It took decades to optimize the circuits themselves. Here's a 1.7 millimeter by 1.7 by 1.2 centimeter chips. And here's one with 2 chips for the JAWS to optimize the microwave circuits for those devices, the materials in the junctions, and the fabrication processes, and then all of the instrumentation and cryogenics. The very early systems were in liquid helium probes in a liquid helium dewar, like I showed on the first slide, where we're just testing chips, but customers could not use those. It took many years to build these chips and turn them into useful systems that any technician can use, and they don't need expertise in the cryogenics or the microwave biasing or the fabrication of superconductors or operation of them. They basically connect their devices that they want to test to the output voltage leads, and then we've automated the systems to make sure they're operating on their quantum states, and we created software to calibrate specific instruments that our customers want. So we've done everything from the device physics, optimization and materials, to the system integration, to packaging them into systems that are useful and people can use. And we sell these as standard reference instruments around the world, probably 40 or 50 of them. They're not cheap because the cryogenics keep getting more expensive, and so do the pulse generators and so forth. But we provide these as a product, and that's how we disseminate standards. So why is that important? Why do we care about quantum standards? For centuries, or at least back into the 1800s, voltage was calibrated and disseminated using what we call an artifact standard. This is an image of an actual battery called a Weston cell that's got cadmium and mercury in it. And they made these as identical as possible to each other. They would make hundreds of these. They would have incredible engineering and manufacturing to create these by hand, essentially, with the same amounts of materials and structures, and put them in boxes that were not sensitive to temperature and humidity. And they could get agreement between them to parts in 10 to the 4 between labs, or parts in 10 to the 5 within their own labs. But you would have to compare these with an unideal standards somewhere else. When the Josephson effect was discovered, people immediately realized that even at 10 millivolts, they could get 2 orders of magnitude improvement in agreement internally or with other labs by just comparing 10 millivolts. And of course, the higher the voltage you get, you can produce as a quantum standard, the better your uncertainty gets. And it took this many years, 25 or so, to improve these conventional Josephson standard circuits to get them to be 10 volts, to get another 2 orders of magnitude. And with these programmable standards that have more utility, we achieved yet another order of magnitude in improvement for comparison, parts in 10 to the 11th. And that's comparing 2 voltage standards in separate cryogenic environments and measuring them at room temperature, measuring the voltages at room temperature. So that's why this is important. These quantum standards are all identical as long as they're behaving in a quantum state, as long as you measure that they are operating on a quantum locking range for the entire device. And so anyone who has a quantum voltage standard can produce the same accurate voltages. You don't need to compare it with the calibration chain to other artifacts. And these standards themselves, sorry about these words moving off the page. The quantum electrical standards, the the quantum Hall effect and the Josephson effect were essential for eliminating the kilogram mass final artifact standard and redefining the International System of Units, not in terms of artifacts anymore, but by defining the fundamental constants as actual value numbers. So that happened in 2018. And the quantum electrical standards helped to measure the current in a mechanical to electrical balance comparator that measured that mass, and it could not have been done. The kilogram became defined in terms of Planck's constant because the quantum Hall and Josephson effects both are related to Planck's constant. So that's really important, and our quantum standards were used in a number of different labs. So what's hard about this? The hard thing for making a practical standard is that h over 2e is a small number. It's 2 microvolts approximately per gigahertz. So if you drive a junction with 20 gigahertz, it's only generating 20 microvolts, and people want to calibrate things at 1 volt or 10 volts because that's where Zener references that are commercially available are producing, and that's what instruments like to have for their references. So you need large series arrays of junctions. So imagine stacking a lot of these junctions in series, just like you do a series array of batteries in one of your old flashlights to increase the output voltage. And again, now we have the number of junctions to increase our output voltage by putting them all in series. So why is this hard? Well, if you look at these curves on the right, there's 3 different junction current voltage characteristics, green, red, and black. They're all driven with the common microwave frequency, so they're generating the same constant voltage, but they don't overlap precisely in current. You can't use a single common DC current bias to bias 3 of those 3 junctions in series to get a quantized voltage. The quantum locking ranges of each junction do not overlap. So that's the challenge, to make the junctions as similar as possible, not perfectly identical, so that you can you can put hundreds of thousands of them in series and drive them at frequencies like 10 or 20 gigahertz to get to 10 volts with just a few DC current biases. So you need uniform junctions, you need to distribute microwave power to them all uniformly, and so forth. So this is what the challenge is. The Josephson effect itself is perfect. It generates the steps at the same voltages. You just got to make a useful system out of them by improving the uniformity. Does that make sense to everyone?
Yeah.
All right, great. So let's move a little faster here. The PJBS system works like this. You take a large series array, you divide it into a binary or ternary sequence of smaller subarrays, 1, 3, 9, etc. And you can bias each of those subarrays to either the plus step, the 0, or the minus step. So it has 3 states, each subarray, and you can program the output voltage as you wish to either positive or negative voltages. In fact, most of our systems have symmetric arrays of junctions. So you can bias half on a plus step and half on the negative step. That allows you to use the lowest voltage range of a voltmeter to measure 0 and confirm that the quantum locking ranges of each side are identical and you're generating perfect quantum state. And we actually use that, and I'll show you that here in a second. It took many years to develop the right barrier material. We use amorphous niobium doped silicon, and this allows us to use co-sputtered barriers of niobium and silicon where we can change the concentration of the niobium to produce any type of junction we want for all of these devices we do, from qubits to voltage standards. And this is an example of the chip with 16 arrays in parallel for the microwaves. They're all connected in series of 265,000 junctions to generate plus or minus 2 volts. So this is how we package them. Even the packaging took effort so that we could interchange these with customers when they damaged them or they blew up for some reason from static electricity because they didn't ground things properly, etc. So that's all technology that took effort, including the integration into a system so that everything's automated, from the optimization of the device with the microwaves, and the cryogenics and the programming of the systems. So here's data from those 16 arrays measuring the output voltage zoomed in at 625 millivolts as a function of bias current around 8 milliamps. And you can see within the measurement noise that we're using here that the steps, the n=1 steps, are flat over a range of 2 milliamps. This is our quantum locking range. And you can see they're all operating. So you could bias the entire array with a single current bias anywhere along this 2 milliamp range. And that also defines how much current you could source out of this device. Here's an example of how the quantum lock, there's not just a quantum locking range in terms of DC current bias from its design point, but also in terms of the microwave power and also in terms of the operating temperature. And this is data measured. You can watch the voltage as the crosshairs of the biases move around this this thing. I'm supposed to be able to play this for you, but I guess it's not playing. I'm sorry. But this white region shows the quantum locking range as a function of both of these parameters. And if you move it off a small amount, a few microvolts of difference can easily be detected with the two halves of the array being measured at both voltages. All right, so let's move on to waveform synthesis. Now we're moving on to JAWS. And as I mentioned before, we're doing digital synthesis with quantized pulses. But to start with, we choose a waveform we want to synthesize. We then put that into a modulator algorithm and calculate the ones and zeros or the three states that we want to use to generate that. And we use this high-speed digital to analog converter to generate current pulses that then are applied to our Josephson junctions. And those junctions then perfectly quantize it and generate a perfect digital stream with the voltage of each pulse being the number of junctions in series that we've created, and you get a perfectly calculable, a perfect measured output spectrum that's identical to the calculable one from the digital bit stream that we applied. So no other devices can do this to generate a perfectly calculable RMS voltage signal here at 10 kilohertz. We still have digital synthesis harmonic content that needs to be handled with low pass filters and so on, but you can see this is 160 dB from the tone to the next few harmonics of the digital spectrum. So these are actual signals that are important, and the noise floor is even farther down because we're generating a 4-volt signal. So this is another example of a measurement that's only at 2 volts using 2 different arrays back in 2016. We're generating a 1 kilohertz tone here in blue, and with the device not being biased at all, we get this green noise floor. And so you can see the measurement has this, when we start generating the pulses, we get a perfect sine wave at 1 kilohertz and 2 volts. And this harmonic content that generated is actually not the digitization harmonics that I showed you in the previous slide, but the nonlinearity of the analog to digital converter that's measuring this. And so this is actually a measurement of the nonlinearity and imperfections of the ADC of the measurement. So here is a perfect 2-volt RMS signal, and it has a 1 milliamp quantum locking range where it generates exactly this image. So here's another plot now at 4 volts RMS. Here we have log scales on both the voltage and frequency. And again, you can see the harmonic distortion from the ADC. And here we are plotting both the period of the digitized waveform and the DC current bias. And this is basically a milliamp current range. And this is supposed to be able to play, but I guess I don't have that turned on. I'm sorry. Oh no. Oh no. Sorry about that. All right, we're gonna have to move a little bit faster here. So let's move on to RF jaws. Again, this is to calibrate devices at megahertz and gigahertz frequencies. This is harder again because for the DC voltage standard and the audio frequency signals, we're dealing with instruments that have high input impedance, like ADCs or DACs. And these Josephson standards are perfect voltage sources for those types of instruments. But when we start going to the RF range, everything is 50 ohms for impedance matching. And so any 50 ohm load that we drive is then pulling current. That current then is, of course, traveling through transmission lines and so forth. So we have voltage drops. And so you don't always, at room temperature, measure exactly the signal that you are generating perfectly across the chip where it's superconducting. So those are challenges. But here on the left, we have our audio frequency jaws that we provide as a standard reference instrument. And we're developing both one at VHF frequencies up to 300 megahertz and also at gigahertz frequencies using different types of RF circuits and design techniques and so forth. And we've had a number of PhD theses working to help us improve these devices. And I'll show you some data from a couple of those in a second. So here for our VHF band circuits, every one of these plots on the right is at the top plot is the deviation in calculated voltage on the vertical axis as a function of the DC current through the devices. So these are essentially flat quantum locking ranges over the DC range. They're not exactly the voltages we intended because of the nonlinear response of the spectrum analyzers and amplifiers we're using to measure them. But another way to see it, not just in terms of amplitude, but is in the total harmonic distortion plotted here in this graph. Again, the total harmonic distortion depends on the nonlinearities that are being integrated from the ADCs that are measured. But they're usually constant over the quantum locking range. And here you can see each of these has a flat total harmonic distortion along a plus or minus 800 microamp current range. So these QLRs are very important for determining where we have quantized pulses being generated in all of the junctions, and the sensitivity of either the voltage or the total harmonic distortion allows us to determine where that range of either pulse amplitude biases or DC biases are occurring. Here's another plot on the bottom left. This is again the circuit and the same graphs you saw before. But here I'm plotting the quantum locking range as a function of frequency on the vertical axis for the same DC current range. And so you can see this one device is producing quantum lock behavior waveform synthesis from a kilohertz up to 50 megahertz using the same bias conditions. And this is, again, measuring the total harmonic distortion, not the amplitude. So that's what you want. And if we don't have good quantum locking ranges, other people can't use them that are non-experts. Here's an example of another circuit operating at gigahertz frequencies, generating a 2 millivolt signal. On the top plot, we have the output voltage of the fundamental. And on the bottom, we again have the total harmonic distortion. And you can see that the quantum locking range here is again 2 milliamps. And again, as a function of frequency up to 3 gigahertz, we have at least a 2 milliamp locking range on DC bias. So that's what we search for. This device itself has 1,500 junctions in series. Akim Babenko, working here as a graduate student for Zoya Popovich here in Boulder. This was his last paper where he helped us advance to getting 20 millivolts RMS at gigahertz frequencies for those circuits. And he, in enjoyed making more complicated waveforms. On the left, we have in the time domain here a chirp signal made with 101 different tones, all centered around a one gigahertz carrier frequency, and on this side, a 10 megahertz QPSK signal for communications, sending data information. And here we have the calculated Fourier transforms of both. And on the bottom, we have the measured spectral measurements of the actual physically generated signals from the circuit. And you can see perfectly spaced uniform amplitudes here, and on the QPSK, amplitudes that perfectly resemble exactly the frequency spectrum expected from the QPSK signals. And you can look up these papers on IEEE. So let's move on to Josephson pulse generators. We did a number of different experiments with Rob McDermott at Wisconsin and Britton Plord at the University of Syracuse, and then went on to do some other examples. I won't tell you about all of that work, but the idea again is to exploit quantized pulses that are perfectly reproducible, don't need to be recalibrated because you just need to put the biases so that they're on a quantum locking range. And if you generate a single pulse and run it through a number of splitters a few times, you can generate a larger pulse on the output that's synthesized and at an amplitude that you wish, that you can then drive other electronics with, like a qubit. And so this is what the circuit looks like here. There are DC to single flux quantum converter circuits and splitters and multipliers and inductive filters to bias them, input coplanar waveguides and output signals and so forth. And on the top here, you can see the DC current bias to this circuit vertically as we change the pulse rate from the DC to SFQ converter, working all the way up to almost 30 gigahertz. So the simulation at 0 and 4 Kelvin are blue and red, and the measured quantum locking range is a dashed black line. And here you can see a perfectly generated 4 gigahertz sine wave, which is essentially made with these quantized pulses operating over a quantum locking range of 100 microamps. So if we take this device, and this is just a generalization, instead of a JOS or DC standard, we have a Josephson pulse generator. We take a sine wave to generate a periodic stream of pulses, and we use that, and we bias it over some quantum locking range. We can actually change the state of a superconducting qubit and rotate it using a fixed number of pulses to change its state. And there's a number of different papers we've done over the last 4 or 5 years that describe these results. This is the most recent one where we've actually controlled a transmon qubit. This is an image of it that we built again using our own fabrication processes. These are some of the characteristics of the qubit, including Rabi oscillations, setting up the JAWS or JPJ device so it operates between 2 and 3 milliamps, and how many periods you choose to drive the qubit with it. And here's a scan of the Rabi oscillations by changing the bias current through this pulse generator. And you can see a quantum locking range that's again similar to the quantum locking range shown here, showing the Rabi oscillations being mostly flat as a function of time. And this measurement of the probability is at this where this red dashed line is created. So let's encourage you to look up that paper if you wish. So finally, let's talk about the Josephson sampler. We just started this, I think, in 2022, originally collaborating with Bart here, who did some of the early work, even with Steve Steve Whiteley at Hypers. We're continuing to work on this now. And this is I don't have time to really talk about the circuits, but we generate a strobe. We have a comparator of junctions, and our device under test. The signal we're trying to measure with the sampler is a periodic sequence of pulses from this DC to SFQ converter. It's our device under test. And this is what the device looks like, the different parts of it on the circuit. So the DCFQ converter is over here, the comparator junctions are here. Each of these circles is a junction with different areas, a different critical current, and so forth. And here is the package that it's mounted in. Here is the system in our laboratory. This is the cold stage. So the device is here in this sample box with RF signals. It's on a dry cryostat cooler in this lab. There's another blue force fridge over here that will eventually put this sampler in and try to measure signals driving the qubit at millikelvin temperatures. For information, we've designed junctions that can operate at these low temperatures and have the performance we need, because we can tune the barriers. So here's how we're verifying the quantum locking range of the pulsar, and we can generate either a single SFQ pulse or a double SFQ pulse. And here's the measurement of the double SFQ pulse using the sampler circuit, biased here at when it's generating 2 pulses periodically. And we were able to get a resolution high enough that we can identify a 3 picosecond wide pulse. So we're very excited about that. There's lots of work to do yet, but optimizing that pulse, the sampler circuit for our process and for timing and phase resolution is really important. So that's the end of my talk. I hope you got an appreciation for metrology, for voltage standards from DC to gigahertz frequencies, what's important about using quantized pulses to control circuits and to do sampled measurements at cryogenic temperatures. Thank you very much.
Yeah. And the talk is open for questioning. Let me check chat. I don't see
a picture of my group. Here's my group.
Okay, well,